let's look at an example of a combined loading problem. So we're looking at this part here, and it has multiple loads acting on it, and we're trying to figure out where the critical location for the stress would be and where that part might fail. So here we have this cantilevered bar, and it has three different forces acting on it. So we have a force in the positive x direction, and here this bar is being loaded here at this end point. So we have a force in the x direction of 75 pounds, a force in the negative y direction of 200 pounds, and a force in the z direction of 100 pounds. So typically when I'm doing these problems, I'm trying to see, conceptually, what is the influence of each of these forces and where would each of them individually cause the part to fail. So if I look first at this force in the x direction, that is causing a moment about the y-axis, so it's causing a rotation about this y-axis. And we also see that the 100-pound force in the z direction is also causing a moment about the y-axis. So both of these would be causing this bending stress about the y-axis. So the critical location would be on the sides here or here, but it would probably be on this side with the negative z direction because the x force is also causing an axial stress. Now, if we look at the force in the negative y direction, we know that that would cause a bending stress about the z-axis, and that maximum would occur either at the top or bottom of the bar. So we can guess here that the critical location, if we were looking at a cross section of it here in the YZ plane, we would see that the critical locations are these 2 points for the two bending moments. And so the resultant would be a critical axis for that bending moment somewhere over here, which would mean that the critical location for the stress is going to be 90 degrees from that. But now we can go about solving for where this critical location actually is in terms of the exact location of it. So to do that, first we need to calculate the moments about the y and z axes. So first we can calculate the moment about the y-axis. So that would be my is going to be equal to the 100-pound force, and that is going to be at a distance of, so the 6 inches plus the 2 inches, so 8 inches. And that is going to cause a moment in the negative y direction based on our right-hand rule. And then we also have the force in the x direction, and this is also going to cause a negative moment based on our right-hand rule. So the 75 pounds, here the moment arm is 5 inches. And so we see a total moment in the y direction of negative 1,175 pound inches. Next, we can find the moment about the z-axis, and that is going to be 200 pounds in the negative y direction. And this is also going to be at this distance of 8 inches. So we would see negative 1,600 pound inches. So now we have two moments, and we need to find how do they combine together to form a resultant moment. And so this resultant is going to be equal to if the square root of the two moments squared and summed together. So we'd have 1175 squared plus the 1,600 squared, and that is going to equal 1,985 pound inches. So we know that's the magnitude of the resultant moment, but now we need to find this direction. Let's draw a new cross section here. And so we know that we have the moment, so draw our axes here and z. And we know that this is occurring in the negative y direction and the negative z direction. So you know that this resultant moment is going to be somewhere in this direction. And so to find what that is, we can define this angle as theta and use the inverse tangent to find what the angle actually is. So if we have the inverse tangent of the my over mz, so we substitute the 1175 in for the my and the negative 1600 in for the mz, and that is what our theta will equal. So our theta here is going to be equal to 36.3 degrees, and that is from the negative z-axis. Now this is just the angle to where this moment is acting about. That's not the critical location of our stresses. The critical location is going to be 90 degrees from that. So we would have some line here. So the critical location could be either here or here, but we know that it's going to be about where the side with the tension is going to occur. So it's going to be up over here. So this is our critical location. And so we know that would be, we take this point and we add 90 degrees to it, and it's going to end up being 36.3 degrees clockwise from the positive y-axis. And so we know that is going to be our critical location and where the part would most likely fail. Next, we need to be able to figure out what does the stress element look like at that location. We've figured out the bending moment, so that will be probably the largest contributor of stress at this location. We also need to figure out the axial stress due to this 75-pound force and the torsion due to this 200-pound force. So we have the 200-pound force that we need to worry about, and we need to figure out the influence of this 75-pound force. So first, let's do our axial stress. So this is just going to be our force over the area. So that would be 75 pounds all over our pi r squared. So we just have 0.5 squared because we know that this is a 1-inch diameter. That will equal 95 psi. So the axial stress is going to contribute very little compared to what we'll calculate for the bending stress in just a moment. So if we do calculate our bending stress now, that would be equal to our mc over I. So that will be equal to the 1985 pound-inch moment. Our c is going to be 1/2 the diameter, or 0.5 inches, and I is pi d to the fourth, so it's just 1 inch to the fourth, all over 64. And this will equal 20.2 kpsi. So much bigger than the axial force. And then the final stress we need to calculate is our torsion. So this is going to be equal to a TR or TC over J, depending on what book you look at for the formula. So in this case, our torque is going to be equal to the 200 pounds, and it's going to be, the moment arm there is 5 inches. Our radius is 0.5 inches, and this is going to be all over pi d to the fourth. So our diameter is 1, so 1 to the fourth, all over 32. And that will be equal to 5.1 kpsi. So now we have all of our stresses that we needed to calculate, and now we can draw what is happening with our stress element. If we have all of our stresses here, we can draw this critical stress element now. We know in our x direction, we have the axial stress and the bending stress, and those are just going to add together. So we'd have this 20.3 kpsi is our sigma, and then our torsion. Now to figure out the direction, so we had this 200-pound force going in in the negative y direction, and so we know that that is causing a rotation this way, and then there is going to be a reaction at the base going the other direction. So I start and I draw the torsion and the shear stress arrow going in the direction of that torque, and then I draw the arrow for the reaction, and then I know that because we need to be in static equilibrium, I can draw the other two arrows that way so that everything would balance out. And we would know that that shear stress is going to be equal to 5.09 kpsi. And that would be what is happening with our stress element. And now we need to go on and find what are the principal stresses at this location. So if we know that our sigma x is going to be 22.3 kpsi, and our shear stress is 5.09 or 5.1 kpsi. So to calculate our principal stresses, we have our sigma x here. Our sigma x was equal to 20.3 kpsi, and our shear stress was equal to 5.09 or 5.1 kpsi. So now we can use the principal stress equation here of sigma 1 and sigma 2 are equal to, in this case, just sigma x over 2 because we don't have a sigma y, plus or minus the square root of sigma x over 2, again because we don't have a sigma y, plus our shear stress squared. And so this is going to be equal to 20.3 divided by 2 plus or minus the square root of 20.3 over 2 quantity squared plus 5.1 squared. And that would equal 21.5 kpsi for sigma 1. And sigma 2 is going to be negative 1.20 kpsi. And our shear stress would either be just the portion of this, or here we can do sigma 1 minus sigma 2 divided by 2, and we would end up with 11.4 kpsi. So now we have our principal stresses, and now we need to understand, is this part going to fail here? So to do that, we can use distortion energy theory and calculate the von Mises stress. To calculate our von Mises stress, we would have our sigma prime is going to be equal to sigma x squared minus sigma x times sigma y plus sigma y squared plus 3 tau xy squared, all to the 1/2 power, or you could put that all under a square root. Now we don't have a sigma y, so those terms will go away. We would be left with 20.3 squared plus 3 times 5.1 squared, all to the 1/2 power. This would be equal to 22.14 kpsi. So that is equal to 22.14 kpsi. And now to apply that and figure out what our safety factor is, we would have our yield strength over the von Mises stress. And our yield strength is 40 kpsi, and that's going to be all over the 22.14 kpsi. And we see that that would be equal to 1.8 as our safety factor. So 1.8 is not very high for a safety factor, so we would consider this to be safe, but there's not a lot of margin for error here since we see that it's less than 2. My overall process for the combined loading looks like this. First, I see the influence of the forces. And I try to understand conceptually what is happening due to each of the forces individually, and where would the part fail due to each of these forces on their own. Then I will find the critical location and resultant moments. Because usually in parts like this, the bending stress is going to dominate. So it's really important that we find the resultant moment and where that critical location is. Then I find any axial and torsion stress. From there, I can sketch my stress element. Find the principal stresses. And finally, I can check for failure with one of our failure theories like distortion energy or maximum shear stress. And this is the process I go through for most of my combined loading problems. Whenever I encounter a part or a problem where I need to take into account multiple forces and understand where a part might fail and what the stress values are at that location.